Yes, this one says that photograph one shows a power supply for some electrical require equipments, and the electrical equipment is connected to the mains supply. So this explain why the power supply is completely covered with plastic. The reason why it is covered with plastic is for the safety procedure, right? Because plastic is an insulator, right? The plastic doesn't conduct electricity. So if there is any fault in your power supply, right, because of the plastic casing, you will never be able to, like, get electrocuted over here, because if, like, obviously we have what we have your electrical components at the inside of your power supply, right? But all the electrical components are well hidden inside your plastic casing. So if all the electrical components, if something is even wrong in the with the electrical components, you will never be able to be in contact with them because they have a insulator layer on them, right? Plastic is the insulation layer on them. It prevents the user from getting electrocuted. It prevents that user to get an electric shock, right? So it kind of acts as a what was that? It kind of acts as a safety procedure, right? Without this, there is a chance that you might get electrocuted with these situations, right? So always it's a better thing that all the electrical components are always covered with plastic casing. That's why your electrical switchboards or charger, everything is always covered with plastic body, right? Because plastic is actually a very, very good form of insulator. It doesn't allow the, like, any user to get electrocuted over here. So you can just say that this is, by the way, a repeated question over here, right? That why all electrical components should be covered with plastic is because plastic is a good insulator, good electrical insulator, and therefore it prevents from getting further electric shock. So I just write this down. The plastic is a good electric insulator and it prevents from further electric shock. On the other hand, if it was connected with your metal casing, then that would be a very big problem because metal cases have the ability to conduct electricity. They are good conductors, they're not good insulators. And that way, it will again create some problem, right? So obviously, the plastic casing is very important. Then again, it says that we have to create an equation. This one, by the way, supplies a 230 voltage. Always use the exact term used in the question, which is power, current, and voltage. I know the formula here is power equals to current times voltage, right? I hope both of you are understanding. This one was quite easy. We just have to, like, write down the formula that we memorized. And it says the electrical component has a power of 350 watt. Calculate the current in the equipment when it is being used. Calculate the current means that we have to find out the current. They have provided you the voltage. They have provided you the power. So if I want to make, I mean, if I want to calculate current, I have to make current the subject. That way the equation looks like this. Power over voltage. How much is your power? 350. How much is your voltage? That is 250. So you just have to divide 350 with 230 and you get 1.52. Okay, but again, as you can see, how many significant figure was used? Two significant figure. So I'm getting actually 1.5217, a very big value. I should write my answer as two significant figures. So I'm going to write my answer over here as 1.5 amp, right? The unit is already given here in this space, so I'm not going to repeat the unit. But if the unit was not given, I was supposed to write ampere here. Is this clear? So far, any questions? Hatim, Amra, any questions? Can you guys listen to me?
No questions, miss.
Okay. Hatim, I hope you're in class and there's no problem from your side. Photograph 2 shows a circuit breaker. Explain the advantages of using a circuit breaker rather than a fuse. Again, a very repetitive questions. What are the, over here, just focus on the question. What are the advantages of using circuit breaker rather than the use? That means, that rather than the fuse. That means you have to say that why is circuit breaker better than the use, right? So basically advantages for circuit breaker and disadvantages for fuse. So I can say that circuit breaker is actually a faster procedure, like it can prevent the large current to flow into the circuit at a faster rate, because for fuse you have to melt that thin wire, then only the current connection will stop. Melting requires much more time than how the circuit breaker works. So that's why circuit breaker works at a faster rate or at a faster speed compared to your fuse. And then again, circuit breaker can be reusable. Like you can just reset the button and then you can use the same circuit breaker multiple times. But for fuse, once the fuse blows, once the fuse melts, I cannot reuse them, right? I have to replace them. That's obviously expensive then. So circuit breakers are resettable or reusable, and fuse is not resettable, reusable. They are replaceable, right? I have to always replace them, throw out the used one and replace it with a new one. So you can see these things that, okay, circuit breaker is first faster at isolating circuit, and or circuit breaker is more sensitive. Over here, you can say more sensitive to change in current, and it is resettable or reused over here, and resettable multiple times, right? We don't have any limitations for circuit breaker. Are more sensitive, and circuit breaker are more sensitive, and they are also resettable multiple times, right? That's your answer over here. Is this clear? This is a repetitive question, by the way. So make sure you memorize the mark scheme points over here. The mark scheme points are more sensitive, can isolate the circuit faster, and resettable. Right? These are all the mark scheme point for this question. I know they're giving you only 3 marks, but you can also write. They're giving you 2 marks, but you can obviously write 3 mark scheme point for this question. I hope there is no problem. I'll just move on to the next question. If you guys have any problem, please raise your hand. This one, it says the student investigates how different electrical components. The student first investigates how the voltage of a diode affects the current of the diode. And then over here, what was the case? The student first investigates how the voltage for the diode affects its current, right? So basically the relationship between voltage and current. For this type of investigation type of question, I always ask you to identify the independent and dependent quantities, right? In this situation, I understand that first in a circuit, I have to provide voltage, then only current arrives. So whenever I want to find out the relationship between voltage and current, voltage is always your independent variable, and this is your dependent variable, right? And now I move forward with the question. In order to prove this, that how changing voltage will also affect the current flow in this diode, we have to use these equipments. We are obviously using diode. We are using a cell for the power supply, variable resistor to modify the resistance of a circuit, connecting wires to make a circuit, then again voltmeter to measure the voltage across the diode, and ammeter to measure the current across the diode or current in the circuit over here. So we have to represent all of these components and create a circuit for this diode over here. Okay, we can do that. I'm using cell over here specifically. So this is a diode already given. So this is your cell, right? I'm not going to use multiple lines over here. We're only going to use just one cell over here. This cell is connected to your diode. Right, then this is how the cell would look. It was not mentioned that over here you have to use a switch and something, but I was using ammeter. Ammeter should always be connected in series. So we are going to connect an ammeter here in series. Then I was using a variable resistor, right? So variable resistor should be always in front of the diode. Now in this case, current always moves from what? The plus terminal to the minus terminal. So not in front of the diode, we can actually connect the ammeter here also, that's possible. So this is your variable resistor with this arrow indicating this is your variable resistor. Then again, I was also measuring the voltage across the diode, right? So exactly across the diode, you have to connect a voltmeter in parallel this time, not in series, in parallel. Voltmeter, right? So this is how the entire circuit looks. And just make sure that you have included everything. They talk about uh, cell, diode, variable resistor, wires, voltmeter, ammeter. We did everything, right? This is your wire, ammeter, variable resistor, voltmeter, diode, cell. Everything is included over here. So you'll get the full marks for this question. Now, if you move forward, they are again asking that in the second investigation now, like in the second investigation, the student uses the circuit with two different resistors and A and B. Like this is your case. Now the student uses this circuit with resistors A and B, and they have a voltage of like both of them. By the way, they're connected in parallel as you can see, right? Because this is a junction here. This is a junction. And in this junction, we have two pathways, right? And they have like again two currents. Resistor A is receiving 0.15 ampere and resistor B is receiving 0.23 ampere. And both of the entire parallel combination is connected in series with this 2.9 volt. So we have to calculate the current in the battery, like the total current in this circuit, right? Actually, this is a much more complicated diagram for this kind of cases. Since I know that, there was no other wires present or other components present other than A and B, I could have easily drawn this as this way. This is your resistor A and this is your resistor B. Right, now in this diagram, it kind of looks much more simpler than the diagram one. And you can see that, okay, your total EMF is 2.9. Current 1 is your 0.15 amp. Current 2 is your 0.23 amp. Now we know for parallel circuits, what were the equations? For parallel circuit, I know that all of them will have the same voltage, but everyone will have the different current and or current gets divided. So I'll just write this down. For parallel circuit, this case was that, what was that? For voltage, everyone receives the same current voltage. So voltage 1, voltage 2, total voltage, everyone is same. For current, that's actually different. Current gets divided here. That's why the total current is the summation of the individual currents of each branch. For example, branch 1 is receiving 0.515 and branch 2 is receiving 0.23. Their summation will give you the total voltage, total current, right? And for resistor, this is how the equation was for resistor. It was 1 by R total plus 1 by R1 plus 1 by R2. Right, these are the three equations for parallel circuit. Whenever in a question paper you see that you're working with parallel combinations, always think of these three equations because they will obviously come handy in order to solve that question. So over here, when they're asking for what is the total current, I'm going to use my second equation here, right? I1, I2 gives you the value for the total current. This is, by the way, I1 for your circuit. This is your I2 for this circuit, and I'm looking for I total, like the total current passing through this circuit, right? So I have the equation already. I total is equals to I1 plus, this is plus I2, which is now 0.15 plus 0.23. That's 1523, which is 0.3 ampere, 38 ampere, right? Is there any problem understanding this question? Hatim, Amra, can you please reply?
No, miss.
Okay. Then if we move on to the next part, is easy. They were just asking to link the equations for voltage, current, and resistance, which we can do that. Over here, we just have to write voltage equals to current times resistance. Then find out the resistance of resistor A, right? Resistor A means this one, right? I want to find out the resistance of this. I know for branch 1 or for this branch, they are receiving 0.15 ampere, and I know that all of them are connected in parallel, right? So everyone is having the same voltage. Total voltage is 2.9. This one will have a 2.9 voltage. This one will also have a 2.9 voltage. So if I just focus on the branch 1, this is what I'm considering as branch 1. So for branch 1, I have the voltage across branch 1, I have the current across branch 1. So I can easily make resistance the subject, and it will be V by I, which is, by the way, 2.9 over 0.15. So we get 2.9, 0.15, and that turns out to be 19.33. So I'll just write this as 19.3 ohms, right? So we get 19.3 ohms, right? This is your case for current. So yeah, resistance of branch 1. Now, if I move down a little bit, they are saying this is again a different case. So I'll be moving on to the next case. Any problem from this question, from this part B? Hatim, Amra, any problem from this question?
No, teacher.
Okay. Then very important to memorize this. Okay. Then again, if you move forward, now I can see a series circuit here, right? As I can see, both A and B are now connected using the same wire to the power supply. So this is a series circuit for no doubt. And for series circuit, even before moving on to the question, I want to talk about that how the resistance is splitted, or how the current and voltage are represented in series circuit. For current now, they all have the same current. So I can write current total is equals to current 1 plus current 2. Then again for voltage, I have your voltage total is equals to voltage 1 plus voltage 2. Now the voltage gets divided in series circuit. That's why their individual components voltage sum up to give you the total voltage. And by the way, this is your total voltage, right? So this two's voltage will sum up to give you 2.9. And for the resistance, it's again the same. R total is actually the summation of the individual resistance in the circuit. So R1 plus R2 gives you R total. After this, it says that, okay, resistor B has a resistance of 13 ohms now. This is of 13 ohms. Comment on the difference between current in the battery in diagram 2. Okay, then, sorry, in diagram 2 and the current in the battery in diagram 1. You use calculations to support your answer. Okay. Mm. If I'm using the same resistors, right? Don't you think that this should have the same resistors also? Like how we calculated the resistance of A as 19.3. So in this equation also, the resistance of A is going to be 9.3, right? No doubt in that. That's a common thing, right? And if you want to find out the resistance of B, I actually have to focus on the diagram 1 to find out the resistance of B. No problem, I can actually calculate that one, and then I can calculate the total current in my second circuit, right? If I have the individual resistance, I can find out use the resistance to find out the current in this second circuit. And after I'm done calculating their different cases, different values, then I can find out their what um, yeah, I can then compare that, okay, which diagram shows which current and all. So use calculations in your answer means that, I have to focus on diagram 1, find out the resistance, and then move forward. So main thing is that, 1 minute, we have 2.9, 0.23. 1 minute. Mm, 12.6 ohm. And current was over here was 0.38. And right, so you can just see from diagram 1, since you're focusing on diagram 1 a little bit, so you can see that, okay, from diagram 1, what are we using? We're using the resistance of resistor B, which is going to be I by V by I. From diagram 1, we saw that the voltage across resistor B was 2.9 as they were connected in parallel, and current was 0.23, which gave you the value of 2.6 ohm. Okay, and now again we're focusing on from diagram 2. We have the, like, if I want to find out the total current over here, everyone is receiving the total, like everyone is receiving the same voltage. Sorry, everyone is receiving the same current. So if everyone is receiving the same current, I can now calculate, oh wait, yeah, I can now calculate the current A. I can say that, total current in the circuit is equals to current A. And how do you calculate the current in A? The current in A is going to be, the resistance across A was 0.23. And what else? No, 1 minute. The voltage across A, I don't know, because, I have to compare that using the voltage of B. I should have calculated this in this way. Like, I'll find out the total resistance first. Total resistance is your R1 plus R2. So we get your, just 1 minute, please. Sorry, as I was saying, R1 plus R2, right? So how much is your R1? R1 is now, because, I'm considering that they have the same resistors, so they will have the same resistance also. So I know 19.3 and 12.6 is supposed to be added together. So 19.3, 12.6. You get 31.9 ohms. Okay. And now you can find out the total current in this circuit, which is going to be total voltage over total resistance, which is now, over here also total voltage is 2.9. So we get 2.9 divided by 31.9. That gives you 0.090. It's a very big value, but you can approximately write 0.09 ampere. Okay, so if this is your 0.09 ampere, the total current in your circuit 2, the total current in your circuit 1 was how much? 0.38, and this is 0.09. So obviously in series circuit or in diagram 2, the current is smaller than the current in your diagram 1, right? That's your final answer. So we can say that current is smaller in diagram 2. So that's your answer. Like over here, the current was in this circuit was, by the way, 0.38. The total current in this circuit was 0.38 ampere. So we can say that current in diagram 2 is smaller than in diagram 1. You don't specifically have to say that, okay, diagram 2 you have, in diagram 1 they were connected in parallel circuits. In diagram 2 they're connected in series circuit. You don't have to say that. You just have to, by the calculation, you prove that, okay, current in diagram 2 is smaller than in diagram 1. Then that's enough, right? You can also say the difference, like what, by what amount. You can also say by like, how do you calculate the difference? 0.38 minus 0.09. That's by 0.2 ampere, right? So that by 0.2 ampere, smaller current is flowing in diagram 2, right? The difference is 0.29 ampere. That's it. Is this clear?
Yes, teacher.
Any question regarding this part?
No. 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 No.
Sorry, Hatim, I cannot actually listen to you. Are you saying something?
No questions.
Okay. Then that's the end for this question, I think. Right? Yeah. Just 1 minute. Wait, I think, sorry, that's wrong file. Right, in the last class, we are completing electricity and we completed up to this question. Right, yeah.
Miss,
Yes, I'm right.
Miss, do you have like short notes for all the topics?
Short notes. Not exactly. I don't think short notes will be helpful now. But we can give people like some mark scheme points for the repeated questions. Right? That you can go through actually today and tomorrow. I'll send you that after the class. But short notes won't be that much helpful actually here. Okay. Okay. Now in this question, this is from June 14 our paper. This one says a photograph shows an electric heater connected to the mains electricity supply. And okay, this is talking about heater, right? And the circuit the heater connected to is fitted with a circuit breaker, which breaks if the circuit if the which breaks the circuit if the current gets too high. So, given advantages of using a breaker instead of using a fuse. Okay, so I'm going to give you the advantage of using a breaker, so using a circuit breaker instead of a fuse. I think this is a similar type of question we already did in the previous part, right? Obviously circuit breaker are easily resettable, and circuit breaker turns off the electricity more quickly, and it is more sensitive to change in current compared to your fuse, right? So we can repeat the same answer. I think this answer was written already in the previous question. This is the answer, right? So over here, advantages of circuit breaker compared to your fuse is already written, already explained. So I'm not going to write that again. So I'll just copy paste that and just place it over here. Right, this is your final answer. And everything is still the same. That over here it is more sensitive. Isolate the circuit breaker circuit faster. Isolate, you can actually also say that breaks the circuit faster. Right, both fuse and your circuit breaker basically breaks the circuit if there is an excess current passing through the circuit. So they both break the circuit faster, and on the other hand, your circuit breaker is much more faster, resettable. You can reuse them, but for fuse, you always have to replace them, right? So this is your 3 mark scheme point. You can just write them for every question for where the question is asking advantages of circuit breaker over fuse, right? So this is again a repeated question. Okay, now after this, they are asking for the voltage of mains electricity supply is 230 volt. State the formula linking power, current, and voltage. Okay, so obviously this is the normal thing. Is your power equals to current times voltage. Now they're also giving you the current and asking you to find our input power. Answer should be in kilowatt. Okay, so we're obviously using the P is equals to IV, where I is 11 and V is 230, right? So we get 11 into 230, which is like 2530 watt, but I obviously have to divide it with 1000 to convert them into kilowatt, right? So we get like 2.53 now. 53 kilowatt. Right. And then again a statement. It says the circuit breaker has a rating of 16 amp. Suggest a reason why the heater may switch off before it reaches to its normal operating system. Okay, 1 minute. The circuit breaker has a rating of 16. Suggest why the circuit, so why the heater may switch off before it reaches its operating no, oh, wait, normal operating current. The circuit breaker has a rating of 16, right? And the normal operating current of the heater is 11. And just suggest why a reason why the heater may switch off. Problem is that, I mean, your heater over here works efficiently at 11 amp, right? It is obviously smaller than the circuit reading of 16 amp, but maybe there is a chance that the appliance get more hot before reaching that 11 ampere. Right, and therefore, if the appliance is getting it like extremely hot before reaching that normal operating current, then certainly the circuit will break at that point. Right, this is one of the reason. Then you can see that what can you say? Well, this is one of the explanations, but you can also think of other explanations. Maybe inside the circuit breaker, so maybe with this heater, right, you have a fuse also, and that fuse have a reading of have a reading less than 16 ampere. So obviously before reaching the 16 ampere, the heater, so the fuse will melt and again make the circuit incomplete. That is another case. And heater actually runs for, I mean, what is the main purpose of your heater? The main purpose of your heater is to generate heat, right? And to make sure that the surrounding temperature is at a constant temperature. So that, basically your, like, if this is your heater and outside environment is your room, so that the room temperature and the heater temperature are equal. If they are equal, they will reach a equilibrium state and all automatically the heater will turn off, right? That's one example. So this is also another case that maybe the thermostat inside the heater turns off because the temperature of the heater and the surrounding became same. So therefore the heater does not, the heater does not have anything to heat further, so it turns off in that case. Right. This is one of the cases. Actually, I want to go for this last one, that the thermostat turns off the heater when the temperature inside and outside the heater reaches an equilibrium or reaches the same amount. Because all the other cases, for example, the heater will become extremely hot before 11 ampere and will turn off the appliance, or we can say that there was a fuse fitted inside the heater with a reading of less than 16 ampere that will cut off the entire circuit supply. These are all assumptions you are using, right? That I don't know if the circuit have a fuse or not, right? I don't think. 1 minute. Yeah, it says the circuit in the heater is connected to fitted. So it to is fitted with a circuit breaker. In this case, they're only asking that, or they're only giving you the information that this heater is only connected to a circuit breaker. They never mentioned it was connected to a fuse. So it's not going to be a better option. I mean, it's part of your mark scheme point actually, but I don't think that that would be like a much more convenient process. Maybe is applicable for this question, might not apply for other questions. So I'll just want to stick for a situation that will be applicable for all the cases. Right. If the question didn't mention you for fuse, for this question they're applying that okay, the fuse, like inside the heater you have another fuse, and that fuse has a reading of less than 16 ampere. But maybe in another question they're not accepting that, because in the question they never said that a fuse was connected in this circuit. It was clearly stated there is a circuit breaker, but there was no statement indicating that fuse was also inside this heater. So I'll just write that the thermostat turns off when the temperature reaches equilibrium. That will be a basic generalized term. So we can write thermostat mass temperature becomes equal over here. Right? That's not a repeated question, but yeah, this is it. Then again, if we move, it says that we have to draw a circuit and all. In this case, they are asking that a student investigates the voltage current characteristics of an unknown component X, and the student is given the equipment to investigate the component X. Okay, 1 minute. Yeah, then same thing. Voltage current characteristics of that unknown component, right? That means obviously voltage is the independent variable, current is again the dependent variable. The student is given this equipment to investigate the component X, have to use a battery, variable resistor, ammeter, voltmeter, and connecting wires. This is that the diagram shows an incomplete circuit containing the battery and the component X. We have to complete the rest of the diagram, making sure that we include everything over here. Right. Okay. I can say that okay, we have your ammeter in this case. We're going to use a voltmeter. So since current is going to pass from this side, so I'm going to use my voltmeter on this side. So not voltmeter. I have to use my variable resistor, place my variable resistor on this part, right? Because current is actually entering the circuit in this case. I place the variable resistor here so that I can modify the resistance before the component X. I can also write this after component X. That will not create that much of a difference, but I just want to write it down over here. And there's nothing else. I just have to draw a voltmeter in parallel across the component X because I was trying to measure the voltage and current for component X, right? So obviously this is your voltmeter across your component X. That's your voltmeter, right? So we have included the battery, component X, ammeter, connecting wires, variable resistor, and voltmeter, right? So the entire circuit is complete. Now, if you go back and go to this next question, it says this shows our results of this investigation. The graph is already drawn. You just have to draw the line for best fit. I mean, you can easily do that. You just have to eventually what? Just connect all the points over here. Problem is I cannot connect all the points, but I'll just make sure that my first point and last point are at least connecting together, right? That is your line of best fit. That first one and last one is connected together. And if you want, you can also extend this so that it passes through the origin. So you can obviously write it like this because this one is going to pass through the origin. So obviously you can extend this to meet to the origin. That's totally fine. And calculate the resistance of component X when the voltage is 4.2 amp and we have to give the unit. Okay, for 4.2, since you're picking information from the graph, so you obviously have to write, okay, this is your 4.2, right? So you are going to pick informations from the graph, which is your exactly I want to stick for this data, which is 2.5 milliamp. So if I want to find out the resistance, that's going to be voltage over current, 4.2 minus 3, right? Because I obviously have to convert that milliamp to ampere. Yeah, 2.5. So I eventually get 4.2, 2.5, 10 power minus 3, and you will get your answer as 1680. Yes, sorry, I actually had to go somewhere. 1 minute. I'm looking for 4.2, right? Yeah. 4.2 passes from that point. That's approximately 2.5 milliamp. But they are actually allowing the current from the reading from 2.3 to 2.4 over here. What I got is 1680, and they're only allowing current from 2.3 to 2.4. So 1 minute. Yeah, right. This is a problem actually. If I'm going to plot a graph, right, the graph should pass through exactly all the points over here, so that sorry, so that the all the points are actually equally distributed on either side of the line, right? This is how the graph should be more well well written. Just 1 minute. I'm sorry, I was actually sneezing a lot, so I had to turn off my mic. As I was explaining that over here, what was wrong with my previous graph is that I was only collecting the first and the last one, which made sure that all the other points were actually on one side of the graph, right? This one is wrong, this one is correct. This one is wrong because all the other points are now on one side of the graph, and in the bottom one over here is the correct one because now all the points are now equally distributed above and below the graph. So I can say that this is your graph, and now again this time if you want to extend this further, it will not actually pass through the origin, so you should not then extend this further over here. And if over here if I want to find out your 4.2 reading, 4.2 is exactly here, so we get your 4.2. I mean, obviously we'll just connect this over here for all the cases. We are getting this for now. This is again at this point, which is almost 2.4 values over here, right? This is 2.4 this time. So for 2.4, we'll get a different value. If you use 2.4 here, then you get your answer as 1750. That will be acceptable over here in the mark scheme. So we will accept 1750 ohms, right? So we get 1750 ohms. Problem is that in the question, if you look at, every data was given in two significant figure. So 1750 should be better round up to 1800 ohm according to the significant figure used in the question, right? So that's why I'll just round this up to 1800 ohms over here. Then again, after this, it says that which of this is equivalent to 4.2 volt? 4.2 volt, like which of this is equivalent to? Okay. Now we have a formula for voltage, which is energy over charge, right? So voltage is obviously equivalent to joules over coulomb. That means J over C, right? This is the only equivalence things, joules per coulomb. So I can see option D is the only correct answer here from this equation. And now again, the student says the student concludes the component X is a filament lamp. Comment on the student's conclusion. Like, why do you think that over here the entire thing is going to be a filament lamp? If you go back to the question graph over here, we can see that the graph is a what? It's actually for us, it's actually straight line, right? Straight line means that it does obey Hooke's law, but over here they were asking for filament lamp. Actually, the student is wrong, because if it was for a filament lamp, right, then in case for filament, how does the temperature changes? Initially, temperature is very low for a filament, but as time goes by, for a longer period of current passing through the filament lamp, eventually heating effect of current increases the temperature, that increases the resistance. So for a filament lamp, the IV graph was actually of this shape, right, where the resistance was not constant, where the graph was not a straight line, the graph was supposed to be a curve. And eventually, the resistance is supposed to decrease for the IV graph, right? That was supposed to be great C shape for your filament lamp. But I can see over here, it's not a curve, right? It's actually a straight line in this case. And another thing, this was a straight line like this, like 1 minute. This was a straight line that would not pass through the origin. Like if you extend this, you can see it doesn't actually pass through the origin, right? And it also have a, like, straight line over here. Straight line indicates constant gradient, which means it obeys Ohm's law, where I is directly proportional to V. So the graph is not a curve, so I cannot say that this is a filament lamp. And it also obeys Hooke's law. A lamp does not obey Hooke's law, but over here my graph is obeying Hooke's law, so it is most likely a resistor. That's why you have a fixed resistance every time. It is actually a resistor and not a filament lamp, right? So you can see that over here, for filament lamp, the graph was supposed to be a curve, and would not obey Hooke's law. Sorry, Ohm's law, my mistake, and would not obey Ohm's law. Current and voltage are directly proportional. So this must be your component X over here, right? So this is your final answer, that for filament lamp, the graph was supposed to be a curve, and it should not obey Hooke's law. Yeah, Hatim, please go. And then again, this graph obeys Ohm's law, showing current and voltage is proportional for this one. So obviously it must be component X over here, right? Okay. And yeah, that was it for this question. This is a quite different question, because in this case, usually in this type of question, they ask you to, like, explain the shape of the graph, right? If you guys remember the IV graph for filament lamp, the IV graph for object obeying Hooke's law, sorry, Ohm's law, which is ohmic conductor, and then again for thermistor, right? Sorry, thermistor, for thermistor, we don't have the graph. There was a graph for uh, diode, right? These two graph. Make sure you guys know which graph is for which component, so that it doesn't create much confusion. Okay, because this type of graphs is very important for physics. That was for the filament lamp. That was for the ohmic conductor. and this one was for the diode. Any problem from this part from anyone? Amra, any questions from your side? Okay,
No, miss.
then if you move on to the next one, the diagram shows a domestic lighting circuit, 230 mains voltage, and this is actually a parallel combination, right? I can clearly see that this is nothing other than the parallel combination. We have three branches. Switch 1, switch 2, switch 3 separately controls the three branches. In branch 1, we have 22 milliamp. In branch 2, we have 43 milliamp, and in branch 3 we have 17 milliamp. That means the total current here is going to be the combination of I1, I2 and I3, right? Because obviously this is your what? This is your parallel circuit. Over here current gets divided and everyone is receiving your 230 voltage. This one is receiving 230 voltage. This one is receiving 230 voltage. This one is also receiving your 230 voltage. So we have to explain advantage of using this circuit for domestic lighting. Basically, they're asking that what is the advantage of parallel over series, right? This circuit is used parallel, so basically you have to show the advantages of parallel circuit. You can just say that I have individual switch for every bulb, so I can see that the lamps are controlled independently, and because the circuit is a parallel circuit, right? So I can just see this one, that as the circuit is parallel circuit, the lamps can be controlled independently, right? I can control them separately for everyone. That's the advantage. And then again, I can see that when switch 1 is closed, wait, sorry, 1 minute. When switch 1 is closed, the current in the lamp 1 is 22 milliamp, and give a name of the charged particle that moves in an electric current. It's always electrons, right? So I can say that, okay, this is your electrons moving, right? That's a repeated question. Now they're saying that show that lamp 1 has a power of 5 watt. I mean, obviously, we have the equation P is equals to IV. I know that lamp 1 passes, have a current of 22 milliamp and voltage of 230. So we have like 22 into 10 to the power of minus 3 into your 230. I know that everyone had a voltage of 230, so we get a 5.1 watt. Understand that the question says about 5 watt, right? So your answer should never be equals to exactly 5. Your answer should be always approximately equals to 5, right? For example, 5.1 will be approximately equals to 5. So we'll accept 5.1. I will never round this up to 5 watt. Then again, they're asking that now find the energy transferred by lamp 1 for 30 seconds. Energy transfer, they're giving you 3 marks, right? Over here, 3 marks is for energy is equals to power into time. That will be your 5.1 from the previous part. And then again, 30 seconds. You don't need to convert the time here. Time is already in seconds. So you can just, add them over here. And you get eventually a value of like how much 150 joules, like 151.8 something. 1 minute, 5.1 with 30, you get 153 exactly. So 153 joules, so you can just write 153 joules in this space. Now again, they're asking the circuit is connected to the main supply and mains voltage is your 230. We have to explain the term for voltage. We know voltage is basically how much? Wait, sorry, 1 minute. Yeah, sorry. I was actually explaining this one, right? 5.1 into 30, we got 153 joules. Yeah, I was explaining your voltage case. For voltage, in this case, voltage is actually your energy over charge, right? So you just have to explain this one, nothing else, that a voltage is the energy transferred per unit of charge passed through the wire, right? So you can just write that equation in words. So energy transferred per unit of charge passed. Or you can just write per unit of charge, that's fine. Now again, they're asking that switch 1 and 3 are closed now, which turns on lamp 1 and 3, but 2 is off, right? Because only 2 is open, 1 and 3 is on. So calculate the current in the mains supply. Usually for the total current in parallel combination, as I've already stated, it's always I1, I2 and I3. Since switch 2 is open, I2 will be 0. I1 will remain as 22 milliamp, right? 1 minute. Yeah, 22 and 17, but this one will be entirely zero, right? Because switch 2 was open, that means there was no current flowing through that switch 2, right? Or branch 2. So I can say this is going to be just 22 plus 0 plus 17, and that's your 39 milliamp. So you can just write this 39 milliamp over here, right? Nothing else other than this. Yeah, it's that's it then. I don't have anything else. This is a repeated question. And what else? Yeah, that's it, right? Other than this, we don't have that much other things over here. We'll move on to the next question. This is question 11 of the same paper. This one says the photograph shows a power bank used to recharge the battery in an electronic device, and the power bank stores charges. Okay, the main idea is that it stores charges. The charge store can be measured in amp hour, which is 1 amp hour is the amount of charge transferred by a current of 1 ampere in a time of 1 hour. Okay, so calculate the charge stored in coulombs when the charge store is 1 amp hour using the formula. And basically, you have to convert that amp hour into coulomb. Coulomb is actually amp second, right? That's the difference between amp hour and amp second. Amp hour means what? One charge over 1 hour, right? 1 ampere over 1 hour. So 1 ampere into 1 into 3600. That way, we'll convert that time of hour into seconds. So that will be basically 3600 coulomb. So you have your answer as 3600 coulomb, right? Over here, the only difference was the unit actually from hour to second. That was the only difference over here. Then again, if you move forward, this is your electronic device is connected to the power bank, and whilst charging, so recharging, the electronic device receives a constant current of 2.4 ampere and 3.8 into the power of 3 coulomb of charge is restored. This much of charge is transferred. Okay, this is your value for charge. This is your value for current, and calculate the time taken to recharge this electronic device. Answer should be in minutes. Okay, now usually if when I use this equation, q is equals to it, right? I have to now find out what exactly time. So I'm going to use the equation q over t. Usually in this case, time is always measured in second. So if I want to time in minutes, I have to multiply 60 at the end of my answer. So we have your charge as 3.8 10 to the power of 3 divided by 2.4. So you have your answer as 3.8 10 to the power of 3, 2.4 That actually gives you 1583, but obviously we have to multiply them with, wait, if I multiply it further with 60, yeah, I can, no problem with this. So not multiply, divide with 60. This one gives me like 1583 seconds. So 1583 seconds divided by your further 60 is going to be 26.38. So I can write approximately 26 minutes over here. Right, so answer is your 26 minutes. That's it. Then again, they are asking the electronic device is connected to the power bank using a long cable. Suggest how using a long cable affects the time taken to recharge the electronic device when compared to a short cable. Obviously, when I'm using a long cable, the charge needs to travel a larger distance, so it increases the time for the charging capability, right? So that's one problem. So we can see that another thing is that longer cable will have higher yes, longer cable have higher resistance, right? So if longer cable have higher resistance, that means what? For longer cable, current charge or current will be passing very slowly per unit of time, or we can say that so charging current will be less, and therefore time taken will increase. Obviously, for a longer current, it will take more current or more time to, not more current, it will take more time to charge that power bank instead for a shorter current. So we can just say that for a longer current, resistance is high, so current flow will be slow. Obviously, for high resistance, current flow decreases from Q equals to IT. We can now refer that for a smaller current flow, it will now take more time to charge the power bank with longer cable than compared to the short cable. So from this equation, it should now take more time with longer cables, right? It will now take more time to charge the power bank with longer cables. That's it. Then this is your mark scheme point. Just 1 minute. Over here, we're seeing that longer wire have high resistance, and therefore current flow decreases, and therefore it will take more time to charge the power bank, right? So these are your 3 mark scheme point. Make sure this is, by the way, always a repeated question, right? That whenever they say longer coil, longer cable compared to shorter cable, these are the things you always talk about. So you can just write a repeated question also for this question. Then we have a chart or something. It says a student owns 3 electronic devices. Each electronic device stores a different amount of charge, and the table gives some information about the charge stored by the electronic devices and how often they need to be used, or they need to be recharged. Like device A will store a charge of 2.4 amp hour, and once every day is enough for charging. B stores 4.2, and once during the week is enough, and C stores 6.8, that is also once during the week is enough. It says that the power bank stores a maximum of 26.8 milliamp, amp hour, and the student needs to take these 3 electronic devices on the school trip for 1 week. So determine whether the maximum charge of the power bank is enough to recharge the batteries of the 3 electronic devices for the school trip. Okay, if you add all of them, right, for example, I need to charge them for 7 days, but for them, I need to charge them for only once. So I just have to multiply 7 with this one. Otherwise, I'll just add 4.2 and 6.8 once. So we have 2.4 into 7 plus 4.2 plus 6.8. That actually gives you 27.8 amp power, which is 1 amp power exactly greater than the given data, right? Or get greater than the maximum power held by the or stored by the power bank. So I can say that, okay, maybe I cannot use your full capacity over here. I should not use my electronic devices until they reach exactly 0%, but I can use some combination in this case, right? That I can use like, um 1 minute, since device B and C will actually work for how many days, for entirely a week. And 1 minute, 2.4 into 7 gives you 16.8. I need 27.8 amp power for the entire week, which is greater than a 2.6 amp power. And then I can say that the power bank is not sufficient to charge all the devices completely. Completely means from 0 to the max 100% power. So what we can do is that I should not use the device, sorry, not device actually. So I can actually say that devices will not always be completely empty when recharged, right? Like I can just recharge them when they're like 20% or 15%. That way I'm not using 100% of that entire space, right? So that's one case. And I can also say that I can use the devices less. If I'm using the device less, obviously that will make the charge last for a longer time. And that's the possibility actually I can think of. In the mark scheme, they are also writing that I should look for other charging facilities available in the school trip. But that's again a kind of dependent question over here, right? This type of points might or might not be a part of your answers, mark scheme. So I should just say that, I first find out the total charge draining charge requirement for the three devices, if that is equal to the power bank's charge maximum charge. If they are not, then what should be the procedures? We should write your answer in that steps for 4 marks. First one is going to be that total charge for all electronic devices is, you do your calculation here, that 2.4 times 7, add this with your 6.8 and 4.2, which is 27.8 amp hour, which is 1 amp hour greater than the of power bank. Therefore, the student should use the device that would make them last longer. And 1 minute. Yeah, that would make them last longer. So the devices will not be completely empty when recharged, right? When recharged. I'll just stop here for a minute so that you guys can listen to this and then let me know if you have any problem from this part. Okay, I'll just stop here for a minute. Please go over this statement and let me know if you have any problem. Yes, Hatim, you have to join the class at 6 p.m. today again. But I'll actually talk about that at the end of the class, okay? Just 1 minute. Is there any problem from this part? sorry, I didn't realize that my mic was muted. Just noticed that Hatham told me that my mic was muted. As I was explaining, I'll just review this again from the start. This is your graph P, which is for directly proportional because we have a constant gradient and graph passes through the origin, right? This is linearly related because it only has a constant gradient and it does not pass through the origin. The difference between these two graphs is that directly proportional passes through the origin, linearly related does not pass through the origin. Then again for R is actually your for filament lamp. This is why is this for filament lamp? Because over here you have your initially you have high current, but as time passes by, heating effect of current, due to heating effect of current, the current flow will decrease. So this is for filament lamp. And this is not for filament lamp. This is not for decreasing resistance and all. Okay. This one I can see that eventually you have like low current, but as time passes by, your current kind of increases over here. I don't know what type of graph is this. Let's just look at the options. Current directly proportional to time. We saw that for graph P, like the first one, right? And then again, current increasing at a decreasing rate. This one is your graph S. Current increasing at a decreasing rate means what? Because as you can see over here, I have my very steep gradient, and then again the graph becomes much more shallow. So I can see for graph S, initially you have a very high gradient or high current, and finally you have a very low current. I mean, low current means it is still increasing, but previously when it was increasing for maybe what value? Previously it was increasing from like maybe 2 ampere to 8 ampere, right? After some time, the increase in current is like from 9 ampere to 10 ampere, right? You can see that yes, it's still increasing, but the increase in current has a very small difference, like from 2 to 8, 8, 9 to 10. They have a very small difference over here. So we can see that is your graph. Yes, the last one is your indicating the current is still increasing, but at a smaller rate, decreasing rate. Then linear relationship is obviously for the second graph, which was, I think, Q. Yes, Q. And current decreasing at a decreasing rate is simply that exponential graph, which I labeled that as a filament lamp. That was going to be the decreasing at decreasing rate, which is your graph R. Right, this is it only. You can obviously go over these files before the exams tomorrow, and day after tomorrow, because this type of files contains all the questions of this topic. And the class will end in another 10 to 20 minutes, right? It depends on actually I want to finish this like at 1:30 p.m. or for you guys, I think it's like 10:30 a.m. 1 minute. Over here, the student investigates how the current in a 60 ohm resistor. The student wants to investigate how the current in that 60 ohm resistor varies with voltage. Same thing. I'm using the change in current, change in voltage experiment. And these are the equipments I'm going to use: power supply, ammeter, voltmeter, resistor. This is, by the way, a fixed resistor now, right? Because the resistance is fixed over here at 60 ohm, variable resistor, switch, and connecting wire. I have to draw a circuit connecting all of them together. So first thing is that I'm using a power supply of 12 volts. So I have to write 12 volt. Not using any other thing other than the resistor. So I can just write. This one. We have your ampere here. Voltmeter across that your 60 ohm resistor. We have a switch. Right, switch and connecting wires, right? These are the only thing. Ampere, voltmeter, resistor. Oh wait, there's a variable resistor also. I just want to connect them over here. right? This is your variable resistor. And yeah, that's it. We have plotted everything you're supposed to plot from the test. Now, if you move forward, describe a suitable method the student could use for this investigation. I mean, I have to describe the entire investigation here. Hmm. One moment. So if I have to speak about the investigation, I always have to make sure I talk about how I'm changing the variable quantity, right? How am I changing the dependent quantity? And then again, what else? Right, repetitions are supposed to be there, control variables are supposed to be there, and everything, right? So how many marks was this? This was actually a 4 mark question. So we can say that obviously I'm going to change the voltage across my resistor and measure the voltage using that voltmeter, and then again measure the current of the circuit using the ammeter, right? And then again we have to repeat our readings for each voltage. And I'll change my voltage for within the interval of 5 volt, 10 volt, 15 volt, 20 volt, and 25 volt, and I will take multiple readings for each voltage. And then again, obviously I have to switch off the circuit in between the readings so that eventually it doesn't create a heating effect that will increase the resistance of the circuit, right? That is a controlled variable. So I can just say that since I want to find out the relationship for voltage and current across the resistor, I'm going to change the voltage across the fixed resistor and measure the corresponding current and voltage using the voltmeter and ammeter. So we can see that. So just one minute. And measure the current and measure the current and voltage. Just one minute, sir. So across it using the voltmeter and ammeter, and what else? We can say that we need to repeat readings, or sorry, we should write about these students perspective. So we should say that they need to repeat readings. Or no, we can actually say them to repeat. Okay. Readings at each voltage and change voltage with an interval of 5 volt. Change voltage with an interval of 5 volt means I'm basically increasing voltage with 5 difference, right? And then again, after speaking about the control variable, that is resistance of the circuit, or I'm using the temperature of the circuit should be constant. So we should turn off the circuit in between each interval to prevent heating effect of current, right? So we can say that temperature should be kept constant. So the circuit should be turned off. In between the readings. So the circuit should be turned off in between the readings to prevent heating effect of current. Right. So here we spoke about that, how we're changing the dependent and independent variable and how we're also measuring them, right? That is using the ammeter and voltmeter, we're measuring the dependent and independent variable. In this case, if I'm changing the independent variable, what should be the interval? And also saying that the interval difference will be here for the independent variable. And again, we're obviously mentioning about the repeat, increasing the reliability of my experiment, and this is your control variable. Temperature of the circuit should be constant. That is your control variable, right? So whenever I'm writing making a description for the experiment, I have to make sure these 3 points are there for my descriptions at least, right? Obviously, for a 4-mark question, these 3 points are required. Is this clear? Karthik and Amra, any question from this part? Can you guys listen to me? Any questions from this part? Karthik and Amra, any questions? Okay, then we'll move on to the next part. It says that complete the current voltage graph by drawing a line that shows the expected results for this investigation. I will see that it will be a straight line passing through the origin because obviously over here resistance was temperature was constant, so resistance is also supposed to be remain constant. But we must have one specific point. 1 minute. You have a 12-volt battery and 60 ohm resistor here, right? So for 12 ohm battery and 60 ohm resistor, what should be the current for your fixed resistor here? That should be 12 over 60. That would give you 0.2 amp. So for your fixed resistor, this is 1 point that should be stated on your graph. So if you go at point, right, so it should be something like this. Right. This one will only get a full mark because you are obviously using that little point of 12.0.2, and then again over here current is increasing with respect to the voltage, indicating direct relationship, and also passes through the origin. Right. Now if you move on, we see the student repeats the investigation with a 120 resistor. Explain how the current voltage graph for that 120 resistor compares with the current of the 60 ohm resistor. Now we have what? Higher resistance, right? Resistance is the gradient for your resistance, not resistance actually. For example, this one has a gradient of 1 over R, right? So if someone has a higher resistance, they will have a lower gradient actually. Lower gradient means therefore the graph is going to be less steeper, right? Because R is high, then your 1 over R, the entire fraction will be low. But for your current and voltage graph, we don't get the gradient as only resistance, we get the gradient as 1 over R. That's why for a higher current with 120 ohm resistor, I will get lower gradient. Lower gradient means the graph will be shallower, right? So it will be half as steeper than this previous one. So you just have to see that over here. Or we can also say that larger current will result in lower, so larger resistance will result in lower current in the second circuit. So we can speak about all these things that the second circuit have large current. So the second circuit have large current. The second circuit have large current. Yes. Second circuit have large current. The resistance, so not the resistance, the gradient will be gradient of CV, it's not CV, my mistake, IV graph. Is now lower.
What? No.
Sorry, Anda, is there a question? I think the mic is mute, so I'm mute. The second circuit have large current, so the gradient of IV graph is now lower compared to the 60 ohm resistor. And now you can see that also because of high resistance, a smaller current will flow through the second circuit. The second circuit, right? That should be your answer over here.